Welcome back. In this video, we're going to go over something called the estimated standard error. So this video is going to be an extension of the standard error topic. And in the standard error topic, we learned that if someone is taking a random sample and is calculating a sample statistic, like a mean or a proportion, the person will want to get an idea of how accurate that sample statistic is likely to be. In other words, the person will want to get an idea of how well that sample statistic is likely to line up with the true population statistic, which we call the population parameter. And we learned that in that type of a situation, the person can calculate something called a standard error to get an idea of how accurate that sample statistic is likely to be. And we learned that if a person is calculating a sample mean and the person wants to calculate a standard error, the person will get that standard error by dividing the population standard deviation by the square root of the sample size. And if the sample is more than 5% of the population, an extra piece needs to be included on the formula, and which is called the finite population correction. And we learned that if someone is calculating a sample proportion and wants to get a standard error, the person will get that standard error by getting the square root of p times 1 minus p over n. And once again, that correction factor has to be included if the sample is more than 5% of the population. And at this point, you might be wondering, what if someone is calculating a sample mean and wants to calculate a standard error along with it, but simply can't calculate the standard error because the person doesn't know what the population standard deviation equals, and therefore can't complete the formula? And you might be wondering, what if someone is calculating a sample proportion and wants to calculate a standard error to go along with it, but simply can't calculate the standard error because the population proportion P is not available, and the person can't complete the formula without the P? Well, in each of those situations, the person can calculate something called an estimated standard error. And an estimated standard error is basically an estimate of the true standard error, and it's calculated using the data that's available from the selected sample. So in this video, we're gonna go over the estimated standard error for sample mean and the estimated standard error for sample proportion, one at a time. So the estimated standard error for a sample mean is used when a person has calculated the mean of a random sample, and the person wants to calculate a standard error to get an idea of how accurate that sample mean is likely to be, but the person doesn't know the population standard deviation. In this situation, what the person will do is replace the population standard deviation with a sample standard deviation. So what the person will do is calculate the standard deviation of his or her sample, the data values from the sample, and use that sample standard deviation as a substitute for the population standard deviation, which is unknown. So the letter S is sample standard deviation. So in this formula for estimated standard error of a sample mean, the letter S, sample standard deviation, has taken the place of the population standard deviation, which is the sigma. So in statistics, whenever you need a population something to complete a formula and you don't know what it equals, what you do is you calculate the same statistic with your sample. You calculate the sample version of that statistic and you use it as a substitute because the sample version is the next best thing, basically. So in this situation right here, the sample standard deviation is the next best thing when the population standard deviation is unknown. So the sample standard deviation is used as a substitute for the population standard deviation. So let's move ahead so the estimated standard error for a sample proportion is used when a person has taken a random sample and has calculated a sample proportion and wants to calculate a standard error to go along with it, but the person doesn't know the population proportion. And what the person does in this situation is the person uses the sample proportion. What the person does is the person calculates a sample proportion using his or her data and uses that sample proportion as a substitute for the population standard deviation. So you might remember from the standard error topic how this formula used to be p times 1 minus p over n. So the formula for the standard error for sample proportion is actually the square root of p times 1 minus p over n, and p is population proportion. But the estimated standard error for a sample proportion is the same thing, except p hat takes the place of p, and p hat is sample proportion. So, so quickly to recap, when you calculate the estimated standard error for a sample mean, you use a sample standard deviation as a substitute for the population standard deviation. And when you calculate the estimated standard error for sample proportion, you use the sample proportion as a substitute for the population proportion. And in both formulas, the finite population correction is needed if the sampling is being done without replacement and the sample is more than 5% of the population. So that the finite population correction is the extra piece of the formula that you saw when we calculated standard error last time. It's the square root of capital N minus little n over capital N minus 1. So that piece is still needed if the sample is more than 5% of the population. And you might be wondering what I mean when I say sampling is being done without replacement. Well, in every situation that we're covering in this class, the sampling is being done without replacement. And what that means is when a population member has already been selected to be in the sample, that same population member can't appear in the sample a second time. And if so, in the reason why all of the examples I'm covering in this class involve sampling without replacement is because in a real survey situation in which data is being collected from people, from a sample of people, you wouldn't sample with replacement. You would sample without replacement because you would only want a person to appear in the sample one time. You wouldn't want a person to end up in the sample as a duplicate entry. And unless you're studying changes over time, let's say. So I'm making all of my examples without replacement just to be realistic, just to resemble real life data collection situations. Now, if a person did decide to sample with replacement, what that would mean is after a person has been selected to be in the sample, that person is still available. That person is still under consideration and could be selected a second time. So it's like if a person is selected and the person takes the survey, that person is put back into the population. The person is basically replaced back into the population, and that person could now be chosen a second time. And if that person is chosen a second time, once again, that person would be replaced back into the population, and the person could be selected a third time. So if you're sampling with replacement, a person could be selected any number of times. So let's imagine that a person takes a sample of 10 people with replacement. It could actually end up that a certain person is selected 10 times and that one person makes up the entire sample of 10. That could actually happen, even though it's unlikely. So that would be with replacement. So yeah, so now let's move ahead and look at some examples of calculating standard error for sample mean and standard error for sample proportion. So here we have a situation in which there's a certain imaginary population, and the population has 900 people, and the mean age of the population is unknown, and the standard deviation is also unknown, and a certain person wants to, a certain person is interested in what the mean age of this population equals. So the person decides to take a random sample in an effort to estimate the mean age of this population. And the person takes this random sample of 10, and the person gives out a survey and records their 10 ages. And next, the person calculates the mean of the sample by adding the 10 ages and dividing by 10, and the sample mean comes out to 19. And at this point, the person wants to get an idea of how accurate the sample mean of 19 is likely to be. In other words, the person wants to get an idea of how close the sample mean of 19 is to the unknown population mean, which is a question mark. So what the person decides to do is calculate a standard error. But the person can't calculate the actual standard error of the sample mean because the person doesn't know the population standard deviation. So what this person does is the person decides to calculate the estimated standard error of the sample mean. And the first step toward that is getting the sample standard deviation, which is S. So the person calculates the sample standard deviation using the same steps that we followed earlier in our class to get the sample standard deviation. The person subtracts each data value by the mean of the data, which in this case is 19. The person gets deviations, and then the person squares each deviation. In other words, the person multiplies each deviation by itself. So -1 times -1 is 1. Further down here, 0 times 0 is 0. 1 times 1 is 1. So the person multiplies each deviation by itself all the way down and gets these squared deviations. And then the person adds the squared deviations. In this case, we get a total of 9. Then the person divides by n minus 1. Remember that this needs to be done when you're calculating the standard deviation of a sample. So there are 10 data values, and 10 minus 1 is 9. 8 divided by 9 gives you the variance of 0.89 to 2 places. And the standard deviation of the sample is the square root of the variance. So the square root of 0.89 comes out to 0.94, and that's our sample standard deviation, S. At this point, we're ready to calculate the estimated standard error because all we have to do is take the sample standard deviation and divide it by the square root of n. So it's 0.94 divided by the square root of 10. At this point, you're not using n minus 1. That's already over with. The n minus 1 is just part of the way toward getting the S. So once you've already calculated the S and you're getting the standard error, the n minus 1 no longer appears. It's just regular n at this point. That's why I'm showing n right here and not n minus 1. So just watch out for that. That's easy to confuse. So 0.94 divided by square root of 10 is 0.94 divided by 3.16, and it's 0.3 or 0.30 to 2 places. And that's our estimated standard error. And you might be wondering why we're using the shorter version of the formula without the finite population correction at the end. Well, in this situation, the sample isn't more than 5% of the population, because if you divide 10 by 900 and multiply by 100, like we did in the standard error topic, you would see that this sample right here is much less than 5% of the population, and therefore the shorter version is used. So now let's go ahead and go over an example of estimated standard error for sample proportion. So here we have a situation in which there's an imaginary population of 900 people, and a person is interested in what percentage of this population lives with his or her parents. So the person does a survey. The person takes a random sample of 10 and asks each person, do you live with your parents? And records their 10 answers. And after that, the person calculates the proportion of the sample that lives with their parents. And to get this sample proportion, what the person has to do is count the number of people that live with their parents in the sample, which in this case is 7, and then divide that by the sample size of 10. So 7 divided by 10 would be 0.7. So 0.7 is the answer. So basically 70% of the sample live with their parents, which makes sense. It's 7 out of 10. And this sample proportion of 0.7 is an estimate of this question mark. It's an estimate of the unknown population proportion. It's basically the next best thing that the person has because the person can't calculate this proportion out of all 900 people because the person doesn't have the data available to do that. So at this point, the person wants to get an idea of how accurate the sample proportion is likely to be. The person wants to get an idea of how well this 0.7 lines up with the unknown population proportion, which is a question mark. So the person calculates a standard error. But in this situation, the person can't calculate the actual standard error because this population proportion question mark would have to be known to be able to get that. So what the person does is calculates the estimated standard error using the sample proportion p hat. And we already know that p hat is 0.7 in this situation because the proportion of the sample that lives with their parents is 0.7. So our p hat sample proportion is 0.7. We plug that in as a substitute for p. And now we do 0.7 times 1 minus 0.7 over 10. So notice how this formula is almost the same as it was before, except p hat has replaced p. So what we do is 0.7, well, first of all, 1 minus 0.7 in parentheses, that's 0.3. Then 0.7 times 0.3 is 0.21. 0.21 divided by 10 is 0.02 to two places, and the square root of that is 0.14. And at this point, we have our estimated standard error for the sample proportion, and we're finished.